will cover section 3.2, part 2. We're going to start from example 4, but before that, we're going to look at some of the properties of basic logarithms. And we have the property that if you take the logarithm of a number and the base is the same number, you could cancel that out and the result will be a 1. Now, to prove that, we can convert that expression into an exponential expression, which is what you see here. And so remember, I told you when you go from logarithm to exponential, you start with a base, and then we will have b to the power 1 is equal to b. So that proves that property that if we didn't know what this number was, it will be something like b to the power x is equal to b. Since here we don't have an exponent, then we assume that that x is equal to 1. Now the next one is the log of 1. It doesn't matter what base it is, it will always equal to 0. And that one is because if we turn that into an exponential form, we will have b to the power 0, and we know that almost anything raised to the power 0 is equal to 1. So to answer example 4, questions A and B, we will have that here we're taking the log of 7, base 7, and so that cancels out, and the answer will be 1. In this case, we're taking the log of 1, base 5. It doesn't matter what base it is, the answer will be 0. So let's go ahead and look at the inverse properties of logarithms. And in this case, this one is similar to the one that it equals to 1 if we were to not have an exponent, because there's an implied exponent of 1. In this case, we don't know what the exponent is. The exponent is x. So we could use the same idea. Those two will cancel, and the answer will be whatever the exponent that you have here. That will be the answer of the logarithmic expression. In this case, because we have logarithmic and exponential functions being inverses of each other, we could apply the same property. And in this case, if you have a number that is being raised to this exponent, in this case, the exponent is the logarithmic expression. So as long as the base for the exponent and the base for the logarithm is the same idea, you cross it out or cancel it out, or they undo each other, and so the answer will be x. So let's look at example 5. You can see here that we're taking the log of 4, base 4, and so we cross that out, and the answer will be 5. For the other one, for part B, we have 6 being raised to the power log base 6 of 9, so that cancels out, and the answer is just simply 9. So let's move on to the next one. All right, so now what we're going to do is graph the logarithmic function log of x base 2. And for that, we're going to use inverse functions and the notion that we have that inverse functions have the x and y values interchanged, right? Do you guys remember that? So from the previous section 3.1, we were able to graph this function, 2 to the power x, and we know that 2 to the power negative 2 equals 1/4, 2 to the power negative 1 equals 1/2, 2 to the power 0 equals 1, 2 to the power 1 equals 2, 2 to the power 2 equals 4, 2 to the power 3 equals 8. So what I want you to do now is interchange the x and y values for each of these. So you can see that after interchanging the x and y values, we will get coordinates like that. If x is 1/4, the log of 1/4 base 2 is equal to negative 2. If x is equal to 1/2, the log of 1/2 base 2 is equal to negative 1. If x is equal to 1, the log of 1, it doesn't matter what base it is always equal to what? 0. And the log of 2 base 2, remember that property that we just went over? That equals to what? 1. And then let's do one more. So the log of 4 Let me show you this one. I actually like this. The log of 4, we could rewrite 4 base 2, so it will be 2 to the power 2. So if we use that property that we learned on the previous slide, we could cancel that out, and the answer is 2. So even if we didn't have this table to interchange x and y values, I think we're getting to a point where we can find the numbers without the calculator. Of course, with the calculator, you guys are experts at that. Now, if x is equal to 8, let me show you here, the log of 8 base 2 is the same as the log of 2 to the power 3 base 2. So here we can apply that rule, and the answer is 3. So now let's go ahead and graph those points. Remember, the row on top are the x values. So I actually prefer to start with 1, so 1, 0, 2, 1, 4, 2, 8, 3. And then here we have 1/2, -1, 1/4. And do you guys remember how the exponential function actually has a horizontal asymptote, right? The logarithmic function is going to have a vertical asymptote, and that is going to be the y-axis, which as an equation will be x equals 0, vertical line. So now I'm going to connect my points, and just make sure that you do not touch that vertical asymptote, and you'll be okay. Arrows on both ends. And so here we have the two graphs. Well, not exactly. We just have 2b to the power x, but let's just imagine that it is 2 to the power x. So you can see here, here's the graph, the exponential one, and here is that horizontal asymptote that we were talking about. Now, what we can see here that the inverse function, and let's just say that the inverse, it is log of x base 2. So you can see the graph is here, and instead of having a horizontal asymptote, we have that vertical asymptote, and that is there. Another thing that is very important is that an exponential function will have a y-intercept with the coordinates 0, 1, where the logarithmic function is going to have the x-intercept, because remember, we are interchanging the x and y values, so it just makes sense, at 0, 1. Now, just as a review, inverse functions, they are reflected across this line. How do we call this line? Identity function, and that is the equation for it. Don't forget that, identity function, because the input is the same as the output. Here we have another two set of inverse functions reflected, and what is happening here is that the base is less than 1, for example, 1/2, like the graph that we did on back in section 3.1, 1/2 to the power x. And then here in red will be the inverse function of that one. But the same things apply. Logarithmic functions, they do have vertical asymptotes. If there is no shifting in both, the vertical asymptote will be the line x equals 0. Exponential functions, even if the base is less than 1, they will have a horizontal asymptote, which will be the line y equals 0. Okay, so let's go to the next slide. And let's look at the characteristics of those functions, of logarithmic functions. So remember when we went over exponential functions, we had the domain was the set of all real numbers. And the range was from 0 to infinity without including 0. So if you guys notice here for the logarithmic function, the domain is actually the range. of the exponential function. Because remember how we switch or interchange the x and y values. You guys remember that? Okay, so it just makes sense that we already went over how exponentials and logarithmics are inverses of each other, right? So whatever is the range for exponential will be the domain for a logarithmic function. And also, whatever is the range for a logarithmic function will be the the domain of an exponential. So just remember, they are interchanged. And remember how we had that vertical asymptote at right here at x equals 0. So it makes sense that for the domain, we do not include x equals 0, so that's why we use parentheses there. All right? And for the range, we're going to have negative infinity to positive infinity. Now, remember how I went over the exponential functions do have a y-intercept? So logarithmic functions will have an x-intercept, and that will happen at the point 1, 0, because the log of 1 of any base is always equal to 0. There is no y-intercept because instead of that, we do have something called the vertical asymptote, and that is the line. I'm sorry, there is no y-intercept because we have a vertical asymptote, and that is the line x equals 0, or the y-axis. Yes? Maybe. Yes, I did. Thank you, Ruby. Thank you for correcting me. Because I don't know how to edit my videos yet. So it should be 1, 0. Sorry about that. Okay, what else? Oh, if the base of your log is greater than 1, the graph is going to be increasing. And if your base is less than 1 but still positive, then you will have a decreasing function. Same thing as exponential. You could see them here both with a base greater than 1. The exponential is increasing, and the logarithmic function is also increasing. It's just increasing at a slower rate. When your base is less than 1, the exponential decreases, and also the logarithmic decreases. So let's look at the graphs that we have here. There are just some examples. So this is an example. We're going to consider the graph in blue as the parent function. And that is log of x base 4. And so remember, we have that x-intercept at the point 1, 0. And we do have that vertical asymptote, which is the line x equals 0. And the graph in red is going to be a transformation of it. And as you can see, we have a 3 being added to the function, so to the y values. So that makes the graph move upward by 3 units. So this point that used to be on the x-axis now is here. But if you notice, the vertical asymptote did not change. We have the same vertical asymptote. Now the next example, again, the graph in blue is the parent function. We have the same x-intercept at 1, 0. We do have the same vertical asymptote, which is right here, the line x equals 0. And what we're having here for the transformation, you can see in the I know your paper is not color coded, but right here we have that negative sign. And so when that negative sign is outside, I mean outside because it's not in parentheses with the x, That means that you're changing all your y values. For instance, we could take this one here. You're changing your y values from being positive to being negative. And so that is what makes the reflection across the x-axis happen. And I know it might be confusing because you're changing the y values, right, to its opposite sign, but you're actually reflecting across the x-axis. The one that we have here, we have the same parent function here. Well, it's a base 2, but it has the same characteristics. That x-intercept is at the point 1, 0. And now the negative sign is actually with inside the parentheses right here. And when that happens, the x values are the one that change from being positive to being negative. And that is what we call a reflection across the y-axis. Now let's go over this table that has the basic transformations. So vertical translation, we'll have that constant being added or subtracted. If it's we're adding something, the graph will move up. Subtracting, it will move down. You already know what to do. You will either add or subtract to the x or from the x. I'm sorry, to the y or from the y, because you're moving up or down. The next one, horizontal translation, that constant will be inside the parentheses. And it is counterintuitive, so if we're adding a constant, it will move to the left. That means you subtract from x. And if you're subtracting a constant, it's actually going to move to the right. And in that case, you will add to the x coordinate or to the x value. We have the two reflections that we already looked at on the previous slide. We have the reflection, if the negative sign is out here, it will be a reflection above the x-axis. That means you multiply y's by -1. If you have a negative inside the parentheses, then that means you are going to reflect above the y-axis, and that makes that you will have to multiply the x values by -1. Now we also have the stretching, vertical and horizontal. Remember, they are two different things. So for the vertical stretching, you will recognize that when the constant is outside the logarithmic expression, it will look like a coefficient. If that coefficient is greater than 1, the graph will be vertically stretched. And if the coefficient is less than 1, but still positive, that's why we say greater than 0, then the graph will be vertically shrinking. And in this case, you will multiply the y by the constant. And the last one here is the horizontal stretching or shrinking. And this one is counterintuitive again. If the constant is greater than 1, the graph will be horizontally shrinking. If the constant is less than 1, the graph will be horizontally stretching. And that happens because instead of multiplying, you will be dividing. So divide x by c. So let's look at the next slide. The domain of a logarithmic function is the set of all real numbers that are greater than 0. So to do that, I'm going to write it as the same sentence. I'm going to write it in interval notation. So that will be the domain is equal to from 0 to infinity. I'm going to write it in set notation, the same thing. So it will be all x such that x belongs to the set of real numbers and x is greater than 0, without including 0. So to answer a question like this one, find the domain of that function. We have x plus 3 inside. If we were speaking about transformations, we know it's a horizontal shift, right? Is it to the left or to the right? To the left. So our vertical asymptote, instead of being on the y-axis, instead of being here, is going to be shifted 3 units to the left. So it's going to be here. But what we need to do to find the domain is you will take what's inside the parentheses and you will create an inequality similar to this one. So it will be that has to be greater than 0. And then we solve for x, so x must be greater than -3. And if you notice, the equation for our asymptote now, vertical asymptote, it is the line x equals -3. Also, what is the x-intercept of the parent function? Remember, the log of 1 is equal to? 0. So that's the x-intercept of the parent function. But instead of being there, now it's going to be shifted 3 units to the left. So that point will be actually here. 1, 2, 3. And that will be the graph. Not exactly, but, you know, very similar. Let's look at the next problem that we have here, which is example 8. And we have a formula that it is a logarithmic function, and the percentage of adult height attained by a boy who is x years old can be modeled by this formula, where x represents the boy's age from 5 to 15, and f of x represents the percentage of his adult weight. Approximately what percentage of his adult weight, not weight, but height, approximately what percent of his adult height has a boy attained by age 8? So, let me ask you a question first. At birth, how old were you guys when you were born? How many years? 0. 0, right? So if we were to find your height at birth, we will be finding f of 0, right? So that will be 29 plus 48.8. Oops, I can't see the equation. Log of, instead of x, we substitute that with a 0 plus 1. Now let's see what happens here. Here we're going to have log of 0 plus 1, which is, what is 0 plus 1? 1, right? Okay, now 29 plus 48.8, what is the log of 1? Of any base? 0. All right, now what is 48.8 times 0? 0. So the height was 29. Is that in inches or in centimeters?
But it'd be huge if it was like.
Yeah. Because the average is 19.
But this is from age 5 to 15.
No, but that is at age 0. Oh, okay, I get you. So the function can only be used from age 5. Okay, sorry. So then x equals 0 is age 5. Yeah, that would be a huge baby. You don't want to have a baby that size.
At all.
Maybe people who marry basketball players. I don't know. Having a baby who is like 21 inches, 22, that's like a huge baby. Yeah, like an 8-pounder. Who was 8 pounds? Cassandra. You too? Oh my God. All right. So let me reread the problem. So from 5 to 15. Okay. F of x represents the percentage of its adult height. Approximately what percentage of its adult height has the boy attained at age 8? So if we're talking about age 8, what will x need to be? 3, right? Okay. So then we will have to find f of 3, which will be 29 plus 48.8 log of 3 plus 1. Now we could plug this in on the calculator because we cannot get an exact answer of what is the log of 3 plus 1 or the log of 4. What would be the base for that one?
10.
It is 10. So remember, when you don't see a little number for the base, that implies that it is base 10. So let me just get the answer, and that will be the last problem of the day. And so the answer is going to be 76. Yeah, but actually the book is using x equals 8, not x equals 3.
Oh. X represents the boy's age, not the boy's age from 5.
So it was actually 1 plus 8. So anyways, the answer is 70, what did I say? 76. 76. Okay, I'm going to record the rest of 3.3 because we're very close to finishing it, okay? And please watch this, please. Because, yeah, 3.2, I'm sorry, because I will not see you on Friday.
I'm gonna go talk to Sophie now. Because I know Colin stays up there so much.
We're going to go over the properties of common logarithms, and remember, a common logarithm is a logarithm with a base 10. Now, the notation for common logarithm, the 10 is not needed, so whenever you see log without a base, there is an implied 10. So the same properties that we went over on the previous slide, so the log of 1, any base is equal to 0. That also applies to common logarithm. So the log of 1 base 10 is also equal to 0. And remember, that is because b to the power 0 is always equal to 1. If we try with this one, it will be 10 to the power 0 is equal to 1. Then we have log of b base b, that the answer is equal to 1. That property also applies to base 10. Remember, there is an implied 10 here, so log of 10 base 10 is equal to 1. We have the inverse properties, which is if you're taking the log of a number, same base, that crosses out, and the answer is x because one will undo the other. So you get identity function there. Same thing for this one. The answer is x. And those properties transfer to common logarithm, but remember the base is 10, so the log of 10, common log of 10 is also equal to x. 10 raised to the power log base 10 is also equal to x. Now with that, we're going to go ahead and move on to example 9. So we have the magnitude, which is capital R, on the Richter scale of an earthquake of intensity I. So intensity is I, and magnitude is R. It's given by the formula that you see here, where the I sub 0 is the intensity at a barely felt zero level earthquake. So that will be the initial intensity, or the intensity at time 0. That's why we have the sub 0. The earthquake that destroyed San Francisco in 1906 was 10 to the power 8.3 times as intense as a zero level earthquake. So what was its magnitude on the Richter scale? So to find the magnitude, remember magnitude is represented by R, so we're going to use R is equal to the magnitude given at that particular earthquake, which is 10 to, and I'm missing log here, the log, and then we will need the ratio of the intensity given for that earthquake in 1906 divided by the initial intensity. Continuing to solve this problem, I realized that I was not sure how to solve it. So I'm going to go back a little bit, and what I need to do is use a formula that has intensity divided by the initial intensity. And so the only thing that we know here is that the intensity of the earthquake was equal to 10 to the power 8.3. If we follow the formula, that will be the initial intensity. And so one of the things that we have to do is that what goes here is going to be 10 times as intense as a zero level earthquake. So because of that, I'm going to go ahead and multiply this part by I sub 0 because of the statement that we have here. So remember the earthquake that destroyed San Francisco in 1906, it says here was 10 to the power 8.3 times. So that implies multiplication as intense as a zero level earthquake. So after that, we do some simple algebra. So what we do next, you can see that I sub 0 times I sub 0 is equal to 1, so we may say they cancel. And with that, we are with the expression that is reduced log of 10 to the power 8.3. And here we do not have a base, but we know there is an implied 10. So, because it is a common logarithm. So those two following the property that we studied earlier, they will cancel out, and so the answer will become 8.3. And that's something like what you hear on the news, the thermometer of not thermometer, I'm sorry, earthquake of an 8.3 scale. I have heard of earthquakes of a 9 scale. So let's move on to the next one. And now what we're going to do is find the domain for the next two functions. And ln is, well, let's go over that one first. So ln is the abbreviation for natural log. And we did discuss this earlier, but let's do it again. That will be a log of base e. So instead of writing down base e, we use the letters L, N for natural log. So the same properties that we studied earlier, the log of 1, it doesn't matter what base it is equal to 0. That also applies to a natural log. Here we have the property that the log of a number of the same base is equal to 1, so the same thing for ln. In this case, if you have to visualize it, picture that base as e, that cancels out, and so that equals to 1. And then we have the inverse property, so the log of b to the base b will be x. And same thing for ln. Remember that the base is e, so if those two quantities match, then you could select the exponent as your answer. Because one will cancel the other, that's why we're using the word inverse. Here we have b raised to the power log of x base b, and so the answer is x. That also applies for ln. So e raised to the power ln of x will be x. So let's go ahead and go back to example 10, find the domain. And to find the domain, we're going to use the same idea. So we take what's inside we call this the argument. and 3 minus x must be greater than 0. So then we have negative x is greater than negative 3. Now here we want to know what x must be greater than, not negative x. So what I'm going to do is multiply both sides by negative 1. Now every time you multiply by a negative number and you're solving an inequality, you must reverse the inequality sign. So in this case, we will have x is less than negative 3 times negative 1 is positive 3. So the x values must be less than 3. Now for example 10 part B, we will take the same the argument that we have here, but now the difference is that our argument is being squared. And in this case, we will take x minus 3 must be greater, well, square must be greater than 0. So the way I'm going to solve that inequality is by taking this part and say x minus 3 must be greater than 0, or x minus 3 must be less than 0. So what I'm going to get from here is that x must be greater than 3, and also x must be less than 3. So if we were to look at the number line for this problem, every single number will be less than 3 or greater than 3 except for one number. So we want to take all numbers that are greater than 3. That will be everything that is on the right side of 3. And we also want to take all numbers that are less than 3. So that means all the numbers that are on the left side of 3. So in this case, our domain in interval notation will be from negative infinity to 3, parentheses, union, from 3 to infinity. If we want to write it down in set notation, it will be x such that x is a real number, and x does not equal to 3. The only reason that we cannot have 3 as part of the domain is because if we were to substitute a 3 here, we will have 3 minus 3 is equal to 0, and 0 squared is not greater than 0. Lastly, for the last 3 problems, we're going to apply the rules that we see here. And so if we have ln of e squared, remember this one could be rewritten as the log base e of e squared. We use that property, and so the answer will be 2. The next one will be ln of e to the power 7x squared will be log base e of e 7x squared. We can cancel that out, and the answer will become 7x squared. And for the very last one, we have right here, remember this is base e, so we could cancel that out, and the answer will be 7x squared. So let's look at the very last problem. When the outside air temperature is anywhere from 72 to 96 Fahrenheit degrees, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. And we hear a lot of kids being left in their cars, so don't do that when you become a parent. If you look at that graph, you could connect the bars or the arrows, and you will see the pattern of a logarithmic function. Since the temperature is increasing continuously, we use natural log because that represents continuous change. And so we have the function, and now it's being modeled by this equation. And so if f of x is the degrees in Fahrenheit after x minutes, so our independent variable, which is x, will be the number of minutes. Use the function to find the temperature increase to the nearest degree after 50 minutes. How well does the function model the actual increase shown in the figure? So what we need to find here is f of 50. to find the temperature after 50 minutes. You could substitute the x with a 50, plug it in your calculator, and then get the answer. And the answer for that problem, it is equal to 41 approximately, since we are rounding to the nearest degree. So it will be 41 degrees, and they are Fahrenheit. Now, to answer the question, how well does the function model the actual increase? Actually, the models the increase extremely well, because if you look at your graph, it is actually there. After 50 minutes, the temperature will be 41 degrees. Not that it will be 41, but it will increase by 41 degrees. So this is the last problem of the session. Make sure you do your homework, and thank you for watching.